Some molecules have lone pairs, one or more on that central atom. So then we can talk about the geometry of the electron groups, what shape they make, or we can talk about the molecular geometry, which is just looking at where the atoms are. When there are no lone pairs on the central atom, electron and molecular geometries are the same. So if we look at 4 electron groups with 1 lone pair, an example of this would be ammonia. Its Lewis structure would look something like this. 3 hydrogens, and then there's a lone pair. You look at this Lewis structure, and each of these single bonds is a group, and the lone pair is a group. 4 groups. 4 groups make a tetrahedron. Here we have hydrogen atoms at 3 of the corners, and a lone pair at the other. The electron geometry is tetrahedral. There are 4 groups. But the molecular geometry, we're looking at just the atoms. This lone pair is 2 electrons, very tiny, right? So I like to think of that as one of the balloons, but that balloon is invisible. You can't see it. It's there. It's pushing the other electron groups away, but you can't see it when you're just looking at atoms.
So the electron group and molecular group.
The electron geometry and the molecular geometry for this one are going to be different.
But if they don't have lone pairs,
It'll be the same. So I can make this lone pair invisible. I don't know why that is so fun to do, but it really is. It's invisible. It's not that it's gone. Because if I had 4 balloons and I popped one, would it keep this shape? No, it would go trigonal planar. It would flatten out because they could get further away. That lone pair is very much there. It's just invisible. For the molecular geometry, we need a name for this shape. It's called a trigonal pyramid because it's not flat. The angles here would be approximately 109.5 because it's part of a tetrahedron. So here we come to the different amounts of repulsion. So lone pairs are more repulsive than bonding pairs. And we see an illustration here. There's a bonding pair of electrons. They're stuck between the 2 nuclei. A lone pair can spread out and take up more space, and that's why it's more repulsive than a bonding pair is. So ammonia has a tetrahedral electron geometry. If it was ideal, all the angles would be the same, 109.5. But ammonia actually has a bond angle of 107 because the lone pair is more repulsive and pushes the hydrogen atoms a little closer to each other. Again, I don't expect you to remember these exact numbers, but you should be able to predict that this is less than 109.5 and that this angle is greater than 109.5 because lone pairs are the most repulsive. So the other guys would rather be a little closer to each other to get a little more distance from that guy. Let's look at water. We've done Lewis structure for water before. Come on. Just looking at the elements, it's 2 hydrogens and an oxygen, you might think, well, that's going to be linear. But it's not, because there are 2 lone pairs on the oxygen. So when you look at the oxygen, the central atom, and count the number of electron groups, there's 4 groups. 4 groups form a tetrahedron. There's the tetrahedron. 2 of those corners are lone pairs, and 2 are hydrogen atoms. The electron geometry is tetrahedral. When we talk about the molecular geometry, we're going to pretend that the lone pairs are invisible, that we can't see them. They are still there, because if they weren't, water would be linear. But it isn't. It has this shape. And we gave that one a super fancy name, bent. It's just got a crick in it. It's bent. We see the effect of those very repulsive lone pairs on the bond angle. We would expect 109.5 from that tetrahedral geometry of the electron groups. It's actually 104.5, because now we have two lone pairs. And they're going to be even more repulsive. They're going to repel each other big time, and they're going to repel those single bonds. So, lone pair is the strongest repulsion. Then lone pair with a bonding pair, and the least repulsive would be two bonding pairs. So how many lone pairs you have on that central atom affects the bond angles. So let's look at 5 electron groups with lone pairs. So 5 groups makes a trigonal bipyramid. Right? That's the pink and red balloon thing over here. Right? If we have one lone pair, one of those balloons is invisible, is the lone pair. Trigonal bipyramid, not all the bond angles are the same. So the lone pair goes to one of them and not the other. If we put the lone pair in the axial position, it's going to have 90-degree angles with bonding pairs. And it's going to have 3 of those. If we put the lone pair in an axial position, the equatorial position, it's going to have a 90-degree angle with 2 of these, but now 120-degree angles with the others. It has more space here. And so that's what it does. The lone pair will always go to the equatorial position. When we're looking at the electron geometry, it's trigonal bipyramid. The molecular geometry, we call that seesaw. I should have gotten out a model kit. If you turn that on its side, this would be on the ground, and here's one seat, and here's the other seat, and you can imagine it going seesaw, seesaw. Again, really fancy name. What if we have 2 lone pairs? So here we have bromine trifluoride. 2 lone pairs. The second lone pair is also going to go in the equatorial position because there's more space there. Still a trigonal bipyramid electron geometry, looking at the electron groups. Molecular geometry, we say, well, those lone pairs are invisible. How do we describe what's left? Again, tip your head to the side, and that's shaped like a T. T-shaped. Xenon difluoride. There's its Lewis structure. It has 5 electron groups, 3 lone pairs, and 2 bonds. The electron geometry is trigonal bipyramid. The lone pairs are going to go along the equator, the equatorial positions, because that's where they have more space. And then when we look at the molecular geometry, this is actually linear. Six electron groups with lone pairs. So here we have bromine pentafluoride, 1 lone pair and 5 single bonds. That's 6 groups, octahedral electron geometry. In an octahedron, all the angles are the same, and so it doesn't matter where you put the lone pair. We'll put the lone pair in one, and then you've got atoms in the other, and they're all going to have, they'll get slightly squished by that lone pair, but the angles will be close to 90 degrees. The name of this molecular geometry is square pyramid, because we've got a square base that comes up to a point as a pyramid. So that's a square pyramid, as opposed to the trigonal pyramid, where the base is a triangle. If we have two lone pairs, xenon tetrafluoride, so there's two lone pairs here. You put the first lone pair anywhere you want, but the second lone pair will be opposite, because lone pair repulsions are larger than lone pair bonding pair repulsions. So these guys hate each other more than they hate the other guys. So they're going to be on opposite sides of the Earth. When we make those lone pairs invisible, we get this shape, which is square planar. So the shape of the molecule does actually look like the Lewis structure for this one. So here is a table from your textbook, which can be helpful as a reference, but I don't recommend relying on that for how to decide what the geometries are. So this is a nice summary slide. The geometry is determined by the number of electron groups on the central atom, and you figure that out by looking at the Lewis structure. One electron group is any of the following. A lone pair is one group, a single bond is one group, a double bond is one group, a triple bond is one group, a single electron, like you'd see in a free radical, is one group. The geometry of the electron groups is determined by their repulsions. 2 is linear, 3 is trigonal planar, 4 is tetrahedral, 5 is trigonal bipyramid, and 6 is octahedral. The bond angles can vary because of different repulsions between bonding pairs and lone pairs. Lone pairs take up more space, more repulsive, they'll squish other things together.